Okay, so we're going to try to bridge the gap between static electricity and current electricity. All right, so current electricity is what we're going to look at today, and we're going to get hopefully all the way into circuit analysis. Not circus analysis. That's something completely different. So the starting point for this is going to be thinking about a parallel plate system, which we've talked about already. And we're going to imagine that we have some charge stored on one of our plates. Okay, and we're going to talk about how we can access the energy associated with that stored charge. So we're going to represent this again as a ball of positive charge. All right? Now we're going to imagine that between these two plates, we have an insulating material. Okay? That could be air, that could be rubber, that could be glass, something that does not transmit electricity or allow electricity to flow through it. Okay? And we're also going to remind ourselves that we know this is true. Voltage is defined as the amount of energy we have per unit of charge. All right, so units then for energy are joules. If you remember, a joule is a Newton meter. Okay, and charge is measured in coulombs. And this, of course, comes from our definition of work or energy, which is force times distance. Force, of course, is ma. So work is mad, all right? And we want to know how much mad we have for each coulomb of charge that we have, okay? So voltage is newtons per meter per coulomb, all right? Or joules per coulomb. This represents a cell. This could be like, could be like a dry cell, say, or a battery. Usually batteries are many of these like lined up, but the symbol is just a sort of like a couple parallel plates. Positive is always the long one and negative is the short one. As we string cells together, they contribute new voltage. So if we put cells in what's called parallel, their voltages add up. All right. So let's say that the total voltage we have here is 50 volts. So that means every coulomb of charge that we put right here, all right, carries 50 joules worth of potential. Potential means the potential to do work, and work is the ability to apply a force over a distance. All right. Now, right now, this charge is trapped here because there's an insulator preventing it from getting across the potential difference. Okay. You might say again, or be thinking to yourself, what is potential difference again? So I'll just quickly remind you. Let's say we have a stored amount of charge. Say we like charged a balloon up on our hair. Okay, we suck the electrons out of here. This will create a field around here, which will affect any other charges that we bring nearby. If it's a positive charge, okay, that we bring nearby, it will be repelled away from here. So if I push this charge over to here, from here to here, all right, I would have to do work to make it go closer to there, and it would naturally spring itself back if I released it, and on its way back, I might be able to harness the energy that's going to be released, okay? That energy might manifest itself as the velocity of the object, or if I'm smart, and I make it, say, travel through a wire, and I like put like, say, a filament of a bulb on there, as that charge whips back through my filament, it'll dump its energy out as heat. And if it's enough heat, my bulb will glow. Okay? So we're taking that kind of like conceptual idea. I got to push something over here. I'm doing work to make that happen. And when it's over here on its way back, I can harness the potential energy to do other work for me. Now we're just sort of like taking this little situation and we're saying, all right, instead of charging something up like a balloon, we're going to use the natural properties of certain metals to have electrons be pushed or pulled between them. Now, with conventional current, of course, we're always going to talk about positive charge flowing, all right? But we know in the back of our mind, because we understand a little bit about chemistry and we understand a little bit about the physical world, that technically it's electrons that are moving. This is the last time we'll ever mention electrons moving. It's going to be positive charge that moves. How can we allow then this positive charge to get from one plate where it has a high potential to the other plate which has a zero potential, which we might also call, by the way, a ground or the ground, okay? So we say then every bit of charge here has the ability to do 50 joules worth of work. How do we get them? How do we harness that? Can you even think of a way that we might be able to harness the potential energy of this bit of charge that we've stored here? Okay, so the correct answer was given, and that is, if I want to allow this to flow across, I have to give it passageway through a conductive material, all right? Usually that's going to be a wire. So I could literally just take a piece of copper wire and I draw a big fat piece of copper wire. And now nothing prevents this from moving from here to here, okay? So as that happens, if this orange tube represents a big, fat piece of copper wire, okay, and this represents something carrying my charge across, this will zip from one side to the other, all right? It'll essentially spend the energy that it has, the potential energy, likely just as heat. That wire will get hot as the charge moves across from one plate to the other. And once it has done so, we no longer have any potential left, okay? My charge has moved from high to low. We're done. An analogy to this. I like analogies, so I'm going to do a super quick little analogy about what we might want to think about here that might help us consider what we're talking about. And that could be something like a water tower. So if we have a water tower, can't tell if that's, I don't think that's flat. There we go. We'll draw it like this. Okay. We can imagine that if we put water in some sort of raised structure, that water then has potential, has the potential to do work for us, right? We've put it up high. If we attach a piece of pipe to it, like so, and put a little tap on there, and we open the tap up, if we say have a turbine in here, we could have the water flow out and down and go past the turbine, and then we can harness that turbine, say connect it up to some belt or something, and we can make this like, if we're clever, I guess, we could attach it to like a pulley. We could get it to lift something up maybe. So as the water flows down, right, through some linkages and so on, we can make it do work in some other form, right? We can make it run a flour mill. We can make it generate electricity. There's all sorts of different things you could do with the potential energy of raised water, all right? So in a sense, this amount of charge is sort of like the water that we have in here, right? We tend to measure water in little chunks called liters. That's usually what we do. And if we know this is, say, 1 meter high, it's 1 meter off the ground, well, if we know this is true, that the potential energy is equal to m times g times h, we know that 1 liter has a mass of 1 kilogram, right? We could say 1 kilogram of water at a height of 1 meter off the ground. We'll say g is 10 meters per second squared, just to make the math pretty straightforward. And a height of 1 meter, we get 10 joules of potential for every liter of water we put in there, okay? So the potential of water inside our water tower is 10 joules per liter. And really, we could say it's 10 joules per liter per meter. If we doubled the height of the water tower, we made the water tower twice as high, now we'd have 20 joules per liter in there, right? Notice I haven't said anything about the total amount of energy, because it's pretty easy to see that the total amount of energy is going to depend on how many actual liters of water we have, right? If we fill this thing right up, we have more overall energy, but each liter of water can still only do the same amount of work. So regardless of how much water I store in here, the turning rate or the lifting rate of my little system will still be the same, okay? So this is kind of like thinking about like different batteries, let's say. So you know that there are AA, AAA, which I think are a little bit smaller. There's C batteries, which are a little bit fatter, and then there's like the big D batteries, right? Well, all of these have 1.5 volts of potential in them, okay? Their different sizes, though, indicate how much charge they actually like have. So in other words, if I'm using these things to run a circuit, and the circuit's like identical, like say it's like a little flashlight bulb, right? The bigger the battery, the longer it will run for, but no more brightly. Kind of like with this, okay? I could make the water tower tub larger, right? I could add more water to it by making it larger, okay? That does not mean, though, that it's going to make this run any faster. How fast this runs is based only on the height, not how much water we have in here. Okay, so a couple sort of basic principles here before we move on. If we imagine that this is a little turbine inside here, okay? We have a little turbine. We could think of this turbine as resisting the flow of water out of the tube. Okay, so it's resisting the flow of water out of the tube. So the water rolls through here, it flows out the bottom and sprays out the bottom. Okay, and in doing so, it does work for us, right? It does work for us. Let's imagine that the turbine becomes more resistive. In other words, like let's say we double the weight we're trying to lift, right? We make the weight heavier. We make that more resistive. Okay, so we could put a bigger resistor in, or a bigger turbine. Okay, a bigger resistance to the flow. What happens to the flow if everything else stays the same, but the resistor or the turbine gets larger? What happens to the flow of water? Well, I think you'd see it would decrease it, right? The water has to like push past this resistor. It's going to be harder to turn. It's going to turn more slowly, and the flow will decrease. So we could say this, couldn't we? We could say that the amount of resistance as it goes up will decrease the flow. So then the flow would be proportionate to the inverse of resistance. And let's call flow I. Okay? I is the flow rate of the water in, say, liters per second. That's not a bad way to do it, right? Liters per second. If I increase the resistance here, the flow decreases, right? If now, all right, we go back to the original resistor and we make the tower higher, right? We raise up the entire height of the tower here. We push it up, okay? Well, all this stuff changes. My tube, now we'll put our resistor back down here. Sweet animation. Okay. Now the tube is longer through which the water's flowing. There's going to be a higher pressure on my resistor. Okay. If the resistor is the same, what happens to my flow? If I raise up the height of my tower here, I made it taller. Okay. What happens to the rate of flow? It increases, right? So as I raise the potential, right? So now this number's higher. It might have gone to 20 joules per liter, right? Because I made it go higher. And we'll call that V. V and the flow are going to be proportional to each other, assuming the resistor stays the same. Okay? So now kind of the last relationship that we might want to think about is this. Okay? And this is this concept. If, let's say, the flow out the bottom now is what I'm concerned about. We've labeled that as I. The flow at the bottom is what I'm concerned about, okay? And I want to keep that flow the same. If I raise my water tower up higher, that's going to tend to increase the flow. So if I want to keep the same flow, then in proportion to how high I raise my water tower, how much higher I make it, I also have to then increase the resistance of my turbine. So in other words, I've got to like add on to the weight that's happening here, or I've got to make a beefier turbine. So then the last thing to think about, or the last relationship that we would need to talk about, is that idea that if I want to keep a constant I value, I want to keep a constant flow, if I raise up the potential, if I make the water tower taller, in concert with that, I also have to increase the resistance of my turbine. So we would also say this, okay? These things need to change in concert with each other to keep a constant flow out of that system. So if you can understand all of these things, then what they lead to is this concept. Or another way to look at that is this. And you've seen this before. Does anybody know what this is called? Correct. This is called Ohm's law. Now I did Ohm's law here with water, but Ohm's law is actually really for electricity, okay? It talks about how if I have an electric pressure or a potential, what kind of flow I'm going to get, okay, based on the resistance to that flow that I place in a circuit, okay? I like to talk about water towers first because I think it makes this law make more sense. Okay, so we're thinking water, but I've used symbols from electricity, all right? And I just want to make sure that we understand what those units are, right? Okay, so first things first, voltage. Well, voltage is, actually I shouldn't call it voltage. Although we do call it voltage, what it really is potential. Measured in volts, which are really the joules per coulomb of the system. The way to think about this, I think the best way is to think of it as pressure. It's like electric pressure. How much push do we have behind our charge carriers? How much push do we have behind our water? This is flow rate, which is better known as current. And current is measured in terms of amps. And the way to think of amps then is coulombs going by every second, or in our system, how many liters per second are going to be flowing in our hose? How many liters per second we're going to have flowing in our hose? So then the last unit here, this is the resistance. So resistance needs some sort of units. So it would be then volts over amps. Or how many volts we need to get a certain number of amps out of that, right? That's the resistance. If we need a lot of volts to get a really small amount of current, we must have like a pretty stiff turbine in there, right? That resists the flow. If we get a big flow for like not a lot of volts, not a lot of pressure, then we must have a very low resistance, okay? There's very low resistance in our circuit, all right? So in other words, we look at a resistor as how much current we get for a given amount of applied pressure on that thing. So then you're like, okay, fine. We talk about it as water. That's great. What do we really mean though if we're talking non-metaphorically and we're talking now about actual electric currents? Okay. So now we got to kind of like use our imaginations a little bit. Okay, and think about the magic dancing pixies that jump around inside circuits and make things, you know, glow or do what we want them to do, right? So symbols become important here. So let's talk a little bit about symbols before we actually like make the leap into actually solving problems about circuits. So first things first, the way, and we've mentioned it before, to represent the water tower is like this, as a battery, okay? Most of the time, people are going to get lazy. They're not going to draw a whole battery. They'll just draw that, and that's fine. That's good enough, okay? Don't really need another symbol than that, okay? This represents potential, source if you want, or you might just call it a battery. And one part of a battery is a cell. When you do electrochemistry, if you haven't already, you should maybe have, I think. you will set up what are called half cells, join them together into full cells, and you'll be able to figure out between, say, zinc and copper, what sort of voltage you get for a zinc copper half cell, and then you can think about linking those together. If that's gibberish to you, if you're not taking chem, just trust that if you are clever and you're a scientist, you can link up certain metals in a particular way to make them have a voltage across them. And that's exactly what batteries are. They're little enclosed chemical systems that create a potential. It's got to do with, I guess, the electronegativity, maybe, if you want to talk about it that way, of the metals that you're using, or I guess maybe the redox relationships between them. All right, anyway. Then we talk about, in terms of a circuit, connecting it together via wires. Wires are just shown as lines. And they're considered to have no resistance at all, which isn't real. That's not really how it works. But when you're doing a circuit diagram, you will often just ignore the fact that the wires themselves have some resistance in them. Okay. Next thing is a resistor itself. In the old days, resistors used to be drawn like this, as a zigzag. They are no longer drawn like this. This is old school. However, you'll still see this from time to time. The new school way of doing a resistor is much better, in my opinion. It's just a little box. So what sort of things are resistors? What are they? Well, let's think about that. If you've taken electronics, I'm not sure which way they show you, but this is the modern way of doing a resistor. And you would just write its rating on there, like maybe like 5 ohms or like 20 ohms. Oh yeah, and that's something I forgot to tell you back here, was that the volts per amp is actually called an ohm. It's got its own name. Because this law was discovered by Ohm. I think his name's Jorge Simon Ohm, or Jorg Simon Ohm. I'm not even sure how to say it. And then the symbol for an ohm is an omega, which is kind of a cool symbol. Looks like a horseshoe. All right. So 20 ohms, all right, 20 ohms means you need 20 volts across here to get a 1 amp current. Okay, so 20 volts would produce a 1 amp current. That's a way to look at that, right? A 40 volt current would produce 2 amps through this resistor. All right. So what is a resistor like? Well, even though I drew it like a box, a good way to think about it is if I have like a hose or a pipe, and then I put like a crimp in it. Okay, and then I put a hose or a pipe, and I say I want water molecules to travel through here. Well, it's going to be more resistive to their flow in the narrow pipe than it is on either side of it. So this is exactly kind of analogous to what happens in a real resistor. A resistor could be something like, let's say, a stove element, something that you just want to get hot, or the filament in a light bulb. The way to think about it is you have no resistance here and you have no resistance here, right? So that's just representing a wire. We pretend they have no resistance in them. And then when the current or the charge carriers get into the resistor, okay, you think of it as if they are like hitting like an area in a stream with a bunch of islands, okay? So let's see if we can think about drawing this. So this is a wire, okay? This is going to be the resistor, and this is more wire. We think of current as being positive charges, right, coming into this resistor from this side. And we say that once we get into the resistor, there's stuff in the way. Okay? Well, what is that stuff? That stuff is going to be the matter that makes up the resistor itself. All right? So the matter that makes up a resistor, it's got to be metal, or it's usually metal anyway, or maybe like a semiconductor. It's made up of atoms, all right? And as these charges attempt to squeeze by, they sort of meet up with these, you know, these bits of matter, and it slows them down. They have to like squeeze by. And as they squeeze by, okay, if this happens to be a stove element, let's say, the squeezing by will jostle the matter making up the resistor, making it jiggle more, and therefore raising its temperature. So this resistor will start to get hot, right? It will get hot as it resists the flow of current by it. It's a mechanical process. The charge carriers get in there, they bounce against the matter in the resistor, and they make it hot. So something getting hot, right? A resistor getting hot can be useful in certain situations. So for instance, let's talk about a stove element. So a stove element circuit might look something like this. You would put, in North America anyway, sorry, I gotta think of my right numbers. 220 volts is usually what goes into a stove. Now this is AC 220, but you don't have to worry about that right now. We'll just pretend that it's like direct current. We'll talk about the difference maybe in another class. So what happens is, you'll see if you ever look at the cord going to a stove, it's a huge fat cord. It's a big giant copper conductor, super fat, right? The fatter the cord, the lower the actual natural resistance the cord will have. Remember I said wires are considered to have no resistance? Well, that's not really true. A wire is made of matter, so there is some resistance in all wires, no matter how good a conductor they are, and we'll examine that a bit later. So what happens is this. You feed your current into your stove, you turn the switch on for a given element, okay? And you imagine that it's like you have a plus plate here and a minus plate here. You have 220 joules of potential here for every coulomb sitting on this plate. Now you connect one plate to the other through a big spiral that is encased inside a ceramic encasement. Inside that ceramic casement, if you're talking about like a classic electric stove element like the spiral kind that most people probably still have, although now like glass tops and induction stuff's coming along, but I'm just talking about like a standard kind of electric stove with the coiled up element. Inside there is a little wee thin piece of nichrome wire which has a fairly high resistance, and it's quite long. So as the current pushes through here, okay, it's squeezing through, it's interacting with this thin piece of wire, and it's heating it up. It's jostling along past those little islands of charge, pushing through the matter, vibrating them, and eventually, if you put it on max, it gets so hot it turns red, and then you boil your water on it, and by the time you get down here, all the coulombs of charge that have passed through there, all right, have ended up at the ground of our little system right here. So in your home, you run into resistors in a few places. Most resistors that you use either make heat, so this would be like a blow dryer or your oven, okay, or a curling iron or something like that, or they run electric motors. We don't differentiate generally in systems what the actual nature of the resistor is, but really what a resistor is the place where the potential is being accessed, right? So through a resistor, we access the potential, or we access the energy inside the charge that we're pushing through our circuit, okay? So resistors access the energy. There's also some other places, obviously like lights too. Old school lights were just basically a heating filament. They just got so hot they glowed. But modern LED lights don't work on that system. They're semiconductors. So you could actually say electricity and electric potential is being directly converted into light in those systems. And you might say, but my LED light gets hot. That's usually because of the circuitry required, because LED lights only run on DC and they don't run at like household voltage. So there's a bunch of circuitry that needs to go into those things to convert the voltage to DC and to an appropriate level so the light can glow. And that's usually where the heat's coming from. Okay, it's still more efficient than just making a filament heat up, because then most of the energy is lost to heat. But if we had DC access to DC current in our homes, you could have like LED lights that make virtually no heat, and all of the energy comes out in the electromagnetic range of like light. Okay, so we could actually say, yeah, lights now, if they're LED, you can directly access them. But otherwise, old school filament lights are just straight resistors. Okay, so we know this then. V is equal to IR. Okay, let's talk about I just briefly. I, that's current. All right, that's how much charge we have flowing by for a given amount of time. So it's like the coulombs per second. If we watch this circuit right here, current, I, is the number of coulombs going by there every second. Kind of like watching a river, how many like liters go by every second. And then of course voltage, which we've discussed before. Voltage, okay, voltage is equal to the amount of energy we have for a given amount of charge. So units here, of course, coulombs per second. Units here, joules per coulomb. Okay, and I just like writing things, I don't know, this is the way I like to write this. The amount of voltage is equal to the amount of current times the amount of resistance. Or the other way to write that is R is equal to V over I. So there's a relationship between all of these things. So let's try an example problem before we're done. Simple. A 12 volt battery is connected to a circuit with a 4 ohm, let's say a 4 ohm light bulb on it. Calculate the current in the circuit. So let's draw this circuit first. I know I said that we usually don't distinguish what type of resistor it is. That's generally true, but this symbol is the symbol for a light bulb, okay, which is a type of resistor that has its own symbol. Okay, so some things do have their own symbols. We don't have to get too deeply into that. And then one more thing that's sort of important is how do we actually measure current? So in the case of a simple circuit, you'd measure it with something called an ammeter. You might have studied ammeters before. They just look like basically, well, I mean, you can have an ammeter on a multimeter, or you can have a standalone ammeter. I'll show you what one looks like in a little bit. But basically, you put a wire into one terminal on it, and the wire out another terminal, and then they'll usually have like a little screen on it with a needle that swings back and forth depending on what the current is. So an ammeter has to be in the circuit itself, right? Because it has to measure the flow through, so it has to actually be part of the circuit to do so. All right, so we know that V equals IR. I is equal to V over R. So we have a voltage of 12 volts. The resistance is 4 ohms. So we get a 3 amp current. A little follow-up to this might be, what's the power of the bulb? So remind me, what units are we looking for if we're talking about power? Watts. And a watt is what? Right, work per time period, right? And SI then would be joules per second, okay? So the power is pretty handy to find when you're talking about electricity, because it's just current times potential. We'll see why in just a second here. Current is measured in coulombs per second. Volts are measured in joules per coulomb. So I think you can see just by dimensional analysis here, coulombs cross off, and the units we're left with are joules per second. All right. So it's just simply the current times the voltage, right? The number of coulombs going by every second multiplied by how much energy each one carries. So in this case, P equals IV, PIV. The current we said was 3 amps times 12 volts. So we're going to end up with 36 watts. So I've sprinkled in some stuff, right? PIV, VER, these are kind of maybe new. And then the stuff that we looked at earlier. And we're done.